In this lesson, we're going to look at impulse and what happens with change of momentum. You'll learn about the definition of impulse and the equation for impulse. You'll find out how impulse is related to changes in momentum and how the time in a collision affects the amount of force. Finally, we'll use impulse to solve some problems. You learned before that the law of conservation of momentum says that in a closed system, the total momentum before a collision is equal to the total momentum in the system after a collision. The key thing here is it's a closed system with no external forces. Impulse is what happens when there are external forces acting on a system, and they can change the momentum of objects in the system. The definition of impulse is the effect of an external force acting on a system over time. In physics, the symbol we use for impulse is capital letter J. You know that the symbol for force is a capital F and the symbol for time is T, so our equation for impulse is J equals F times T. Impulse equals force times time. The unit for force is the Newton, abbreviated with a capital N, and the unit for time is seconds, abbreviated with a lowercase s. So when we multiply force times time to get impulse, the impulse unit is Newton seconds. There's an interesting and very useful fact about impulse, which is called the impulse momentum theorem, and says that the impulse on a system is equal to the change in momentum of the system. Looking at the equations, we see that J equals delta P, which is change in momentum, which is equal to force times time. All three of those things are equal. Because they're equal, an impulse measurement in newtons per second can be equal to a momentum measurement in kilogram meters per second. If you break them down, those two units actually mean the same things. There's some really interesting and useful applications of impulse in everyday life. These mostly come from the fact that when you spread out the time a collision takes to happen, meaning that you're spreading the impact out over more time, you decrease the force of the impact. And we can see that in the impulse equation. The equation tells us that impulse equals force times time. But what would happen if we were to take the time and make it larger? Since the impulse in a collision is staying the same, if we make the time larger, the force has to get smaller. The opposite is also true. If we make the time of a collision very small, then the force of the collision has to become very large. You can test this idea right where you are. If you jump in the air and land with your legs straight, you're really going to feel the impact because you're stopping quickly and there's a high force. On the other hand, if you bend your knees when you land, you're spreading your impact with the ground out over a longer time, which reduces the force and hurts your knees less. Another experiment with changing the force and time and using the idea of impulse involves an egg, a sheet, and a wall. If you were to throw an egg at a wall, you'd make a mess. The egg's going to break. There's no way around it because when the egg hits the wall, it stops in a very short time and experiences a very high force, and eggs don't like high forces. On the other hand, if you were to hang a sheet in front of the wall and throw the egg at the sheet's going to give, and it slows down the impact over a longer time, and the sheet will actually catch the egg without breaking it. The impulse in both situations is the same, but because you've increased the time by letting the sheet catch the egg, you've reduced the force. This also applies to automobile safety. Modern cars are designed with a crumple zone in the front. This is why you often see a lot of damage in relatively small collisions. The crumple zones are designed to give way in an impact, slowing the collision down and spreading it out over time so that the impact force on the car occupants becomes less. Car airbags do the same thing. In a collision, they provide a buffer zone that slows down the impact to the occupants over time, and it reduces the force on them by increasing the time of the collision. Let's go through some example problems. In the first problem, a stunt plane produces 1,300 newtons of thrust, and it accelerates for 25 seconds to take off. How much does the plane's momentum change during takeoff? To solve the problem, we're going to use our Q's method. K is for the knowns, U for the unknown that we're trying to find, E for the equation, S for substituting, plugging in the knowns into the equation, and then the final S for solving as we show each step. The problem tells us that the plane produces 1,300 newtons of thrust, which is a kind of force, and that it accelerates for 25 seconds. So we have our force and our time. The question in the problem is how much does the plane's momentum change during takeoff? Now, I remember the impulse momentum theorem that tells me that impulse is equal to change in momentum. So I know that I can find impulse from the knowns I have, from force and from time. So I'm going to make impulse my unknown. My equation is J equals F times T. Substituting in the knowns, I have J equals 1,300 newtons times 25 seconds. Multiplying those together, I get J equals 32,500 newton seconds. Now, that's not the answer I'm looking for. I'm looking for the momentum change, but remember the impulse momentum theorem. J equals delta P, or impulse equals change in momentum. Since impulse and change in momentum are equal, my final answer is that change in momentum, delta P, equals 32,500 kilogram meters per second. Remember to change it to units for momentum. Here's another example problem. The Blue Flame rocket car fired its rocket motor for 20 seconds and accelerated to 292 meters per second. The car had a mass of 3,000 kilograms. How much force did the rocket motor deliver? The problem gives us a time of 20 seconds, a velocity of 292 meters per second, and a mass of 3,000 kilograms. The problem asks us to find force, but it doesn't give us enough information to find that directly. However, it does give us a mass and a velocity, which we can use to find momentum. We'll start out using the equation for momentum, P equals m times v, momentum equals mass times velocity. Substituting in the knowns, we get momentum equals 3,000 kilograms times 292 meters per second. If the Blue Flame began from a stop and accelerated to 292 meters per second, it had a change in momentum of 876,000 kilogram meters per second. Since we know that impulse is equal to change in momentum, we can say that impulse, J, is equal to 876,000 newton seconds. Here we're going to bring in a second equation, J equals F times T, and we're going to substitute in our values for J and T. So 876,000 newton seconds equals force times 20 seconds. I'll divide both sides of the equation by 20 seconds to isolate F by itself. And notice that the 20 seconds cancels out on the right-hand side and the seconds cancel out on the left-hand side. Dividing 876,000 newtons by 20, we get our final answer. Force equals 43,800 newtons. In this lesson, we've seen that impulse is the effect of a force acting on a system over time. We've learned that impulse is force multiplied by the time that the force acts, and that impulse is equal to the change in momentum. We saw how spreading a collision over a longer time reduces the force.